In section 9.3, we're going to do the first of two different types of hypothesis tests for two population means. In section 9.3, we're going to do what's called the independent samples test. So if you're kind of following along on your chart, you decide, okay, I've got two populations, I'm going to test a mean, and then you still have one more decision to go, and that is, are you testing with independent samples, and that's section 9.3, or dependent samples, and that's section 9.4. 9.4, dependent samples. Now the independence and dependence really refers to whether or not the values you get in one sample are related to the values you get in the other sample. I mean, I take as one sample the average scores or the scores on test 2 from the left side of class, and I compare that to the scores on the right side of class. Maybe that's not a great example. Let's do that for our class and our class on test 2 and my trig class on test 2. Your scores on those tests are going to be different. All right, they're not related to each other. What you do on your test is not going to be related to what somebody does on a trig test. Now, a different example of something which might be dependent would be if you're testing golf balls and they have you hit a golf ball of brand A and then you hit another golf ball of brand B. How far that ball goes in part is going to depend on the ball. What else is going to depend on? It's depend on you. Yeah, how good you are. So how far that ball goes is not independent from one sample to the next because it's going to depend on your skill. So if you have a dependent case, then you're going to have to do a different type of test. Let's start out here with the independent samples. And you can get extra credit if somebody can blow up Microsoft Word for me. I don't know why that this didn't type out. It should type out as X bar on your handout. Maybe it's a copier problem, in which case, same thing applies, extra credit. Two independent samples, those are your assumptions. That's a big assumption. You want to get that one right. You don't want to test this with stuff from 9.4. That's not going to work for us. Now, one of these two things have to be true. Either both populations are normally distributed, which would be nice, or both samples are large. So that's the alternative. One of those two things has to be true. Either way, what we'll end up with is something that's going to allow us to use a t-distribution, which is kind of like the normal distribution light. Normal distribution with a little bit more uncertainty. Same 6 steps as always. You can see that I'm starting to kind of update my handouts a little bit. Find the critical values of the distribution or go to StatDisk. Analysis, hypothesis test. This time we're going to go to mean 2 independent samples. Select your appropriate your alternative hypothesis. And then one last little catch here, and this is so annoying that there's a lot of little different decisions you're going to have to make. For the most part, you should be selecting unequal variances, no pool. And we'll talk about that in a little bit. But for now, assuming you're going to do StatDisk, test 4 or step 4 really reduces to finding the p-value. And once you know the p-value, you can accept or reject. Actually, accept is not really the right way I should say it. Fail to reject or reject, and then state your conclusion in words. So let's do a couple examples of this. We'll start out with problem number 16 in as much as it relates to a problem that we did in section 9.2. actually, no, maybe it's not 16 that relates. Oh, it is 16. Yeah, sorry, here we go. IQ and light exposures. Dataset 5 in Appendix B lists full IQ scores for random samples of subjects with low lead levels in their blood and another random sample of subjects with high lead levels in their blood. The statistics are summarized below. Use a 5% significance level to test a claim that the mean IQ scores of people with low lead levels is higher than the mean IQ score of people with high lead levels. So they've given us some summary statistics, which is nice. We're not going to have to load that ourselves. And we're going to do a test of whether or not these two means are different. So let's take a look at this last sentence here. Tests a claim that the mean IQ score of people with low lead levels is higher. So that mean here is higher than the mean IQ score of people with high lead levels. So, okay. This is going to be a two population mean test. Now our original claim here in problem number 16 is that the mean level of low blood lead levels is going to have a mean IQ which is greater than that of people with high lead levels, blood lead levels. Yeah, it's a tongue twister here. The null hypothesis would then be the opposite of this, a less than or equal to. We're going to test this at the 5% significance level. That's going to be dictated by the book. And then we've got all the summary statistics that we need. So let me list those here for, they're just in the book. I'll just kind of cut to the chase here. And we'll input them from here. All right, so let's input those into StatDisk. So go to Analysis, Hypothesis Testing, Mean two independent samples. Let's take care of our alternative hypothesis before we forget it. It's an easy thing to forget. It's just a little drop-down menu, but what do we want? Population 1 not equal to population 2, greater than, less than? Which one do you think we want? Greater than. All right, so let's just make sure we enter these in that order. 5% significance level. We're using summary statistics. We don't have all the data in sheets. That's fine. The summary statistics are this. Sample size 1 was, let's see, we've got to be careful. We want to put in the high lead levels here, right? So sample size 1, 21. That actually doesn't quite meet our 30 or more threshold. So what you really should do would be to do a normal probability plot or the Ryan Joyner test to make sure that it is actually a normal distribution. Right now we're just going to make that assumption that it is coming from a normal distribution. High lead levels, I got this wrong. Low lead levels is what we should be doing first. So that's, yeah, that one would be 78. 78 here. Yeah, we want to keep this in order. So 78 with a mean of 92.88. And a standard deviation of 15.34. Notice we put that in as sample standard deviation. We don't know the population standard deviation. Now down to here, our second population. High lead levels, there was 21 people in here. Mean of 86. 0.9, so 86.9. Standard deviation of 8.99. It's interesting that there's a much smaller standard deviation for this group. Now, I said earlier that one of the things we'll look at some point is the pooled variances. For the most part, I would recommend that you go with unequal variances. When you work with equal variances, what that allows you to do is create a more powerful test. You're more likely to reject H naught if it's actually false. So it's nice if you make that assumption, but you really should investigate that assumption. It's not something we're going to do necessarily right now. So let's just keep it unchecked. We'll work with unequal variances. I think I've got everything set in here, so let's do evaluate. Test statistic, critical value, p-value. That's what we're looking for, 0.0132. So the p-value, 0.0132. Bree, what's that telling us we should do about our null hypothesis? Yeah. So the p-value is less than alpha, so reject H naught. Now, was our original claim in the null or alternative hypothesis? It was in the alternative hypothesis. So this is where our original claim was. Let's see how we want to word our conclusion. Original claim does not contain equality, so we're down here. And do we reject it? Yes. We reject it here. So the sample data support the claim that, and then we want to state really what's in the alternative hypothesis. So why don't you try and write it down without looking at what I'm writing it, or what I'm writing. Okay, so you should have something to the effect that the sample data support the claim that the mean IQ of those with low blood lead levels is greater than that of those with high blood lead levels. Let's actually look at the confidence interval related to this as well. So the confidence interval is for the difference in those two means. So if you subtract the mean score of those people with high blood levels from those with low blood lead levels, The difference is thought to be in here someplace between 1.5, about 1.60 and 10.36. So let's write that down. 1.60 less than mu1 minus mu2 less than 10 point, let's just call it 10.6. Was it? Nah, it's bothering me now. 10.36. Yes. You know, the number of decimal places, I think the authors suggest that you use one more than is in your data is the rule of thumb, is the number of decimal places to use here. And as much as we didn't really see the original data, I just used the nearest hundredth. You're talking about IQ, so I don't think you really need to go to thousandths or 10,000ths here. I think hundredths is near enough. Does it make sense that 0 is not in this interval? If 0 was in this interval, what that would be saying is that mu1 minus mu2 equals 0, or if I add mu2 to both sides, mu1 equals mu2. In other words, that confidence interval shouldn't contain 0, because what we concluded is that these two things were different. In fact, we said, you know what? Mean 1 is probably bigger than mean 2. That's what our conclusion is. So 0 should not be in that interval, period. It's not. So kind of like an earlier problem we did today, because this is based off of a one-tailed test, it's doubling that area of alpha in both tails. So this is a 90% confidence interval. You can actually, if you wanted to, go back and reanalyze this and find a confidence interval. Let me just state this for the 90% confidence interval. We can be 90% confident. Notice you're not saying probability. We can be 90% confident that the true difference in mean IQs is between 1.6 and 10.36. Now the actual point estimate of what we would think the true difference is, the actual point estimate is just the difference in these two sample means, 92.88 and 86.9. So a difference of about 5.98, or about 6 points. So that's a pretty big difference. It's a noticeable difference. Okay. Anything on this one? Our first one here from section 9.3. All right, well, let's try one more then. Kind of following our pattern, we'll do a couple of these. Problem number 18. So the nice thing about 18 is it gives us a chance to do one from some data. Listed below are the heights in inches for a simple random sample of supermodels, and you can read all the names there. Appendix B includes the heights of a simple random sample of 40 women from the general population, and here are the stats for those heights. Oh, I guess we're going to do summary statistics again. So 40 women, average height of 63.78, standard deviation of 2.6, Use 1% significance level to test a claim that supermodels have heights with a mean that is greater than the mean height of women in the general population. So what's given here is the mean height of these supermodels. We've got some summary statistics, but we've also got some data. So this is kind of like a little bit of a hybrid problem. Our goal is to test claim that the mean heights of these women is greater than that in the general population. So let's find out. H sub 0, H sub A. So the mean height of supermodels is greater than the mean height of women in the general population, and less than or equal to would be in the null hypothesis. That's our orange claim. Okay, original claim. We're going to test this at the 1% significance level. Let's take a moment and look at our assumptions. One of two things has to be true for each data set. Either they're large samples or they come from a population that is normally distributed. Well, tough to tell in the case of the heights of the supermodels without actually getting our hands on the data and playing with it. So let's enter the data into StatDisk. So I'll clear all this data out. Let's enter in the height of the supermodels. So it's 70, 71, 69.25. Now here's the difference between, self-reported heights and somebody that measures. Somebody that's self-reported would say 69. If you're actually measuring, it's 69.25. Likewise here, 68.5, 69, 70, 71, 70, 70 again, and 69.5. Okay. As part of checking our assumptions, we can check whether or not these look like they're normally distributed. And if you want to kind of cut to the chase, the quick and direct way to do that would be the normality assessment. So go under Data, Normality Assessment. The data is in column 1, so click Evaluate. And it can't reject it. It doesn't look too bad. I'm a little bit unhappy with all these heights here at 70, exactly 70, but you know what? It fails to reject the normality assumption at the 5% and 1% significance level. So we can't throw it out. It's not that bad. So let's go ahead and continue with our hypothesis test. So we checked our assumptions. Let's see. Well, how are we going to do this? Because we need some summary statistics. Yeah, we got to get the summary statistics from the data first, right? So to get those summary statistics, click the Data tab, and then go down to Explore Data. And that's going to give you your descriptive statistics. So Data, Explore Data, Descriptive Statistics. It asks you what column you want. Let's think about that for a second. All right, I'm kidding. It's column 1, right? We have no choice there. And there's all the summary statistics that you could want, including another look at our normal quantile plot and histogram. There's 3 summary statistics that we need here. Does anyone know what they are? Yeah, mean, standard deviation, and sample size. So for the supermodels, let's write those down. The mean is 69.825. How tall is that in feet and inches? Who's quick?
5 feet 9 and
Yeah, 5 feet 9 and 7/8. Well, close to 7/8. So the mean X bar for supermodels is 69.825. Standard deviation S. Let's see, where is it? Standard. There we go. 0.7997. I think we can get away with rounding that to 0.8, just for simplicity. We're not really rounding it all that much at that point. And sample size was 10, so N was 10. Now those same summary statistics for women from the general population were N equals 40. X bar was 63.78. And we'll do the 1.5. And a standard deviation of 2.597. Good, so we've got all our summary statistics. Let's enter this and complete our hypothesis test. Bless you. Wow. You can go to YouTube and listen to that one again. All right. Let's see. So, hypothesis testing. There we go. 2 independent samples. Our alternative hypothesis is that population 1 is going to be greater than population 2 because we're going to put the supermodels here. So there was 10 supermodels. Mean there was 69.825. Standard deviation was 0.8 or 0.7997 if you want to be a little more exact. For population 2, from the general population, 63.7815. Oops, that's wrong. That should be the sample size. Or that's the mean, not the sample size. The sample size was 40. The mean was 63.785. And the standard deviation was 2.597. Again, we don't want to put the population standard deviations because that would result in a different test. Check unequal variances. And then let's significance level. Do we want 0.01 for this one? All right, thank you. Significance level 0.01. Perfect. And evaluate. Wow. So we got a p-value of essentially 0. Dominic, what's that saying we should do with the null hypothesis? We fail to reject or reject? Yeah, reject. What is that p-value of 0.0000 saying to you? Nothing? All right. Nothing? You got nothing. What's that p-value of 0.0000 saying to you? Yeah, it's so small they round it off to 0. I mean, let's look back at the data. Oops, not this one. This one. I mean, I mean, we really almost didn't need to do a statistical test to tell us what we knew. I mean, look at that. There's like a 6-inch difference there between supermodels and the general population. I mean, it's telling you that, look, this isn't even close. Why are you even doing a statistical test? All right. Sometimes you still have to go through and follow through with emotions, but yeah, that one's a no-brainer. Supermodels are taller, period. Okay, so let's state our conclusion then. The original claim was that that did not contain the possibility of equality, so down to here, we rejected. So the sample data support the claim that the heights of supermodels are greater than the heights of women in the general population. I know it's a little bit wordy, but please do follow through on the conclusion carefully. I don't think you have a perspective for how nice it is not having to do this on a graphing calculator, and there's just so many things that we're avoiding. Finding critical values from our distribution, the actual calculation of these test statistics. Even if I was to give this to my calculus students and say, here, put these numbers into your graphing calculator, there's a good chance that people are going to make a mistake putting these things in. So what I'm saying is that we've gotten rid of a lot of stuff, but the one thing that I want to get rid of, and I want you to make sure you're really careful with, is stating the conclusion. So please get that part right. Make sure that it matches your decision, what you have with the p-value, etc. Make sure you get the conclusion worded correctly. Any questions or thoughts on this one here? On the back of your handout, talks a little bit about, if you can pool the standard deviation, then what happens is you're going to get a more powerful test. And your p-value is going to tend to be smaller. You're going to be more likely to reject the null hypothesis. Before you start pooling those things, you really should do a test of whether or not they're actually equal. And we can do that with an F-test that we get at the end of this chapter. But that's not in this section. So, for now, for homework, try problem number 1. And that's it. Just kidding. Sorry. I know, that was cruel. 7 through 19. So that's not too many.